Okay, first of all, let's check, can you hear from home? Let me just check one thing. Okay, so I was just okay. So today we resume from where we left yesterday. So yesterday we discussed how to make how to evaluate a classifier, and we introduced a metric that was able to take into account cost of errors. We have said not all errors are of the same kind, so they may have different costs. We saw how to take into account the application prior probabilities, so a method that is geared towards a given application, and how to normalize it so that it tells us whether our system is actually doing something useful or not. So we introduced the empirical bias risk, and then we saw how to specialize it for binary applications. Now, the second thing that we have seen that for binary problems, it's fairly easy to see how our decisions affect the error rate, in the sense that we have seen that our decision takes typically the form of computing a score and comparing with a threshold, and we have seen that the choice of the threshold directly influences the false positive and the false negative rate. So those samples that are incorrectly classified. And changing the threshold allows us to trade off these two kinds of errors. We have seen ways to visualize how the error trade-off happens when we change the threshold. We still didn't define how to select a threshold that is optimal for our task. A task, we said, for the binary problem is specified by a prior probability and the cost of the two kinds of errors. For multiclass, we will have a cost matrix and a vector of prior probabilities. These tools that we have seen allow us to see how the threshold affects the different error rates, but it doesn't tell us what is the best combination for a given task. For a given task, depending on the cost of errors and the prior probabilities, different false positive and false negative rate will give different values for the bias error. So how do we select the threshold that is optimal for our task? Now, to select the threshold, we need to, well, the threshold selection will come as a solution to the problem of mapping the output of our classifier to a decision. We have said yesterday that decisions are actually actions that may be general. So, for example, take umbrella, not take the umbrella in the case of weather prediction. As a first approximation, we said, okay, here we consider decisions that correspond to labeling the sample with a label that corresponds to a class. But again, what we say is not restricted to just labeling, but to any action that we can take following the answers from our classifier. So we have our actions, and we have a classifier that we built in a probabilistic way. So it's a probabilistic classifier, like, for example, the ones that we have seen up to now. The classifier for a given set of priors, which are the application prior, will give us a set of class posterior probabilities. For multi-class problem, this will be one probability for each class, so we will have a vector of class posterior probabilities. And for a binary problem, we will actually have a single value, because once we know the probability for class 1, we also know the posterior probability for class 1, we also know the posterior probability for class 0. In any case, our classifier gives us posterior probabilities. And we now need to decide which action we should take depending on what the recognizer tells us. Now, of course, we don't know the label, so the only thing that we have access to is the set of class posterior probabilities. The class posterior probabilities tell us what? According to the recognizer, what's the probability that the sample belongs to class 1, or to class 2, or to class 3, and so on. Then we can measure what is. We now need to decide which action to take. Now, for each action, we can measure what would be the expected cost according to this set of probabilities. That is, for example, it's taking the umbrella as cost 1 when it's rainy, as cost 1 when it's sunny, was cost 1.5 when it's snow, and 1.5 when it's rain. To take the umbrella action, then if the probability of sun is 0.7, the probability of snow is 0.2, and the probability of rain is 0.1, I expect that with a probability 0.7, if I take the umbrella with a probability 0.7, I will pay a cost 1. Then with a probability 0.2, I will pay a cost 1.5, and with a probability 0.1, I will pay a cost 1.5. While if the cost of not taking the umbrella is 0 if it's sunny, 5 if it's snow, and 10 if it's rainy, then if I don't take the umbrella, I expect that 70% probability I will pay 0. With 20% probability I will pay 5. With 10% probability, so 0.1, I will pay 10. So the cost that I expect to pay is 2 here and 0.7, 0.15, no, 1.15 here, something like that, maybe, and just something like that. So here, if I don't take the umbrella, I'm paying a higher cost because there is a non-negligible probability that it will rain or snow, and not taking the umbrella in this case is much more expensive, unless I made a mistake in the computations here, but the idea is that one. So in this case, even if the probability that the sun is large, I will still decide to take the umbrella because there is a non-small probability that I will need it, and the inconvenience that I have if I need the umbrella and I don't have it with me, for me, it's large enough that it compensates the benefits that I have if I don't take the umbrella and it's sunny. So what does it mean? It means that for each action, we can compute the cost that we expect to pay if we take that action according to the recognizer probabilities. That's an expectation over classes. We take the cost for action A, we consider all possible assignments of the class label, and then if the class label that was correct was K, we pay a cost CAK, and according to our posterior probability, there is a probability C equal K given X that K is the correct class. So we have a set of probabilities from the point of view of the classifier that tells us what is the probability that the sample belongs to any of these classes. We can use this to compute what's the expected cost that we expect to pay according to our recognizer. So the recognizer tells us what is the probability of all the three classes. I have a cost for my action depending on which is the correct class, I take the expectation of this is the expected cost of taking action A. So we expect that if we take action A, we will pay a cost given by this quantity according to the posterior distribution of the recognizer. Notice that all this depends on the recognizer. It's the expected cost according to recognizer R. Two recognizer R1 and R2 may give me different posterior probabilities. The first one may, for example, give me for sun 0.7, then 0.2 for snow, 0.1 for rain. These are posterior probability given R1. The second one, for the same sample, may give me different values. These are the posterior probabilities according to classifier R2. But in any case, from the point of view of the classifier, since I don't know which thing will happen, I have my own estimate of the probability. The best I can do according to my view, my knowledge of my model of the uncertainty of what will happen is to try to take the action that minimizes cost, the expected cost, according to my knowledge. So here the probabilities, you can see they are not a probability of an event. That's not the probability that tomorrow is sunny, but that's the measure of the probability that recognizer 1 puts over the different events. Recognizer 2 may have a different measure for the probability of those events, because probabilities measure essentially our uncertainty about what will come. So different models, different entities may have different beliefs on what will happen. But there is not such a thing as the probability of tomorrow being sun. There is the probability of tomorrow being sun according to recognizer 1, the probability of tomorrow being sun according to recognizer 2. But in any case, when you take the actions, you always do it in a subjective way. You need to take the actions according to your uncertainty of what will happen. So each recognizer will take actions that are optimal for its own assignments of probabilities to the event. So for each recognizer, I can compute the expected cost of an action, then the optimal decision from the point of view of the recognizer will be to take the action that minimizes the expected cost. For example, if I believe, as before, I deleted it, but that if I take the umbrella with those probabilities, I expect to pay a cost of 1.15. If I don't take it, I expect to pay a cost of 2. Then my optimal decision is take the umbrella, because the expected cost that I will pay for choosing the action is lower. So I will lose more if I don't take the umbrella. Notice that here we cast everything as cost, but we could cast everything as gains. I gain more by not taking the umbrella than I gain by not taking it. We use it cost, but you can always transform cost into gain, because you can add a constant or remove a constant cost from all the actions that a cost that you will pay or a gain that you will get in any case, and then you can cast everything as cost again, as we have done up to now. So we talk about cost, but that's not limiting. So the expected, the bias cost, the optimal decision from the point of view of the recognizer is to take the action that minimizes the expected cost according to the knowledge that the classifier has. Notice that minimizing the expected cost will not minimize in general the expected cost according to the real label of the samples, because we don't know the real label of the samples. And we can't even say that, because if we knew the real label of the samples, then we would know which is the actual action that we should take. We wouldn't need to use a recognizer at all. So the recognizer will have its own view of the world, so its own model of the uncertainty about what will happen, and the optimal decisions are optimal from the point of view of the recognizer. Remember that yesterday we introduced a player that was, we call it E, there was somebody who knows the real labels, the real distribution of the data. Bias cost was a cost that measured how we would perform according to this entity, while the optimal bias decisions are optimal according to the recognizer. They are not necessarily optimal for the evaluator who knows the real label, because the classifier may make mistakes. In any case, we want, since the only information that we have is here, the best we can do is take the minimum expected cost according to the information that we have, which is encoded by the posterior probability given by the recognizer. Now we have here a numerical example that allows us to see how this affects the decision that we make. We have again the problem we discussed yesterday, a three-class problem, where these are the prior probabilities. For now, for this example, we will not need them, but I copied them in any case. And this is the cost matrix. So I recall you that this is the cost of predicting 1 when the label is 1. This is the cost of predicting 1 when the label is 2. And this is the cost of predicting 1 when the label is 3, and so on. Here I have the cost for predicting 2, and here the cost for predicting 3. Now, suppose that we have a recognizer that given a test sample using these prior probabilities somehow, for example, through the Gaussian model or a categorical model. We don't know what is the problem, but let's imagine we have a classifier that at some point gave us these class posterior probabilities. The posterior probability for class 1 is 0.4, for class 2 is 0.25, for class 3 is 0.35. Now, what we were doing up to now, we will say, let's take the class which has highest posterior probability. So for us, this will be label predict label 1. So we would assign it to the first class. But let's now take into account the cost of mistakes. What is the cost of labeling as 1? Well, according to our classifier, if we label as 1, we have 40% probability of being correct. So we have 40% probability of paying 0. If we label as 1 the point, there is 40% probability that the sample is from class 1, according to the recognizer, so there is 40% probability that we will pay a cost 0. However, there is a 25% probability that the sample actually belongs to class 2. What is the cost that we will pay in this case? If we label the sample as 1, but the sample is from class 2, how much we will pay? This is the cost of predicting 1 when the label is 2. It's 1. So with 25% probability, we will pay 1. And then there is a 35% probability that the sample is actually from class 3. If it's from class 3 and we label it as 1, we pay a higher cost because this is a worse mistake according to our cost matrix. So there is 35% probability that we will pay a cost of 2. This from the recognizer point of view. If I label as 1, I have 40% of being correct, 25% of being incorrect, and the actual class is 2, and 35% of being incorrect with the actual class being 3. So in this case, if I make the mistakes according to the probabilities that I have of making these mistakes, this is the cost that I will pay. Result, you have it on the slides, it's 0.95. If these were, for example, euros, it means that if I classify the point as belonging to class 1, I would pay 95 cents. I can repeat it for class 2. For class 2, what do I have? If I label the sample as from class 2, I have 25% of being right, because the point is from class 2, and I will pay 0. But then I have 40% of being wrong, and the sample was actually from class 1. and 35% of being wrong, and the sample is actually from class 3. So again, I will pay a cost of 1. Overall, the cost that I pay if I label as 2 is 0.75. And then finally, the last one, if I label as point as class 3, I have 0.4 probability of being incorrect, and the point is from class 1, which means I will pay a cost of 2, 0.25 of being incorrect because the point is actually from class 2, and I pay a cost of 1, and 0.35 probability of being correct and paying a cost of 0, which is 1.05. Which tells me that which is now the optimal label that I would put to give to the point, to the sample. I will give the label that corresponds to the lowest cost. I want to pay as low as possible. I don't want to pay more than needed. So assigning the sample label 2 results in an expected cost that is lower. Why? Because it's true that I have a higher chance of being incorrect. But if I'm incorrect, the cost that I pay because I did the wrong thing is low. While if I assign, for example, class 1, it's true that there is a higher chance that I'm correct. But there is a high chance that I'm also incorrect in a way that it's much more expensive. So since I have a smaller probability of being incorrect, but being incorrect is much more expensive, that action is not preferable because the second labeling as 2 is actually, it's like saying, okay, when I label as 2, I may be not that correct, but even if I'm wrong, it doesn't matter. So if it doesn't matter because, or it matters a little, it matters just 1. So if it matters a little, if I have an action that I have low chance of being correct, but if I'm wrong, it doesn't matter, I will still take that action, rather than taking one where my mistakes will actually matter. Which means that, in this case, the best solution is to actually take the middle answer as the answer. I may be more wrong, but being wrong has a little impact. So that's the best course of action. With the other two options, I may be less wrong, but if I'm wrong, that's much more expensive. So I prefer to avoid those because if I'm wrong, there is a low probability that I'm wrong, lower probability that I'm wrong. But if I am, I will pay a much higher cost. Now, as we said, the bias decisions are optimal from the point of view of the recognizer. How are they related to the bias risk that we saw yesterday? In both cases, we had an expectation. Here we try to minimize the expected cost of an action. Yesterday, we measured the expected cost of the actions made by the recognizers. Are these two related? The answer is yes. So we said that the recognizer evaluates according to its own distribution of the probabilities, that is the distribution probability of the application data. So somebody who knows the application data. While the recognizer takes its actions to optimize an expected cost where the optimization, the optimality is from the point of view of the recognizer. So recognizers is optimizing the decision when the class assignments are taken according to the recognizer output, while the bias risk is optimizing an expectation where the expectation is taken according to the evaluator view of the world. How these two reconcile? Well, we can show that if the recognizer and the evaluator are the same thing, so we have the same entity, so they have the same distribution, actually our optimal bias decision optimize the bias risk. So optimal decisions are optimal for the bias risk when the decision maker is the same entity as the evaluator. When the distribution that we use to make the decision and the distribution that we use to compute the bias risk are the same, then the optimal bias decision are optimizing also the bias risk. Here you have a sketch of the proof, which is actually based on rewriting the expected cost that we wrote yesterday. By simply taking this joint probability, yesterday we factorized it as a prior times a class conditional, and now we factorize it in the opposite way, a class posterior times a marginal for the samples. If we factorize it in this way, this can be taken outside of the sum, so we have the integration part over the marginal for the samples, and then this part here is what? That's the expectation over the posterior of the cost of the actions taken by the recognizer. Now, if we can replace this expectation over E and R are the same, so the expectation taken over the posterior given by the evaluator is the same as the posterior given by the recognizer, because the two are the same entity, so they give the same posterior probabilities for each of the samples, then we can replace this E here with R. This is an expectation of the cost taken by the recognizer. If at each step we use the optimal bias decision here, then this is minimized, because this is exactly the cost of an optimal bias decision and is always lower or equal than the cost of any other action, because the action is chosen as to minimize exactly the term. The optimal bias decision is the action that minimizes for each sample this internal expectation. That's exactly what we define as the cost, as the expected cost. So the expected cost of an action taken by the recognizer is the expectation over the class posterior probabilities of the cost of taking that action. But the optimal bias, which is exactly this expression, expectation over the posterior of the recognizer of the cost taken by the recognizer. And if we take the optimal bias action, the optimal bias action is the action that minimizes this cost. So for any other action, the cost will actually be higher. So this, for each sample, taking the optimal action is a lower bound, the minimum of this inner expression, which means that the integral is lower bounded by the integral that we get by taking always the best action. So the bias risk is always greater or equal than the bias risk that we will get if the classifier chooses the optimal bias action. This holds when the recognizer and the evaluator are the same. So if the recognizer and the evaluator are the same entity, so they have the same knowledge on the data, then optimal bias decision from the point of view of the recognizer minimize the bias loss, the bias risk of the evaluator, which tells us what? Two things. If our recognizer knows the truth, then optimal bias decisions are also optimal in the sense that they minimize the bias risk. So if an evaluator who knows everything uses his knowledge using our strategy to take decisions, it will also minimize the empirical bias risk. So we will have the lowest value of the empirical bias risk. So the empirical bias risk would be minimized by somebody who has complete knowledge of the data. So we can't do better with, in terms of risk, of somebody who knows everything, and that's a good thing. But we can also interpret in another way. Optimal bias decisions are optimal in the sense that they minimize the bias risk when the bias risk is not evaluated by this evaluator E, but as evaluated by the recognizer himself. So if the recognizer assumes that his knowledge is the best knowledge that you can have on the data, then if you assume that the recognizer itself is the guy who will evaluate the bias risk, so we'll use the recognizer distribution on the data to evaluate the empirical bias risk, optimal bias decisions are also optimal in the sense that they minimize the bias risk as the recognizer would evaluate it. So the optimal decisions are optimal in these two senses. From the point of view of the recognizer, they're the best the recognizer can do. If the recognizer itself was asked to evaluate his own decisions, then the decision that it takes by minimizing the expected cost is the best that he can do to optimize the bias risk from his point of view. He cannot do better than that because from the point of view of the recognizer, the distribution that he has on the data, that's the only information that he can have. He cannot have other information. So from its point of view, that's all he knows about the data. And from the point of view of the recognizer, the optimal bias decisions are optimal because they also minimize the bias risk that the recognizer itself would measure for a given data set. So, as if the evaluation was not made with the real label, but with the knowledge that the recognizer itself has. Question? Now let's go back to our binary problem and see how the optimal bias decisions specialize in this case. Remember, we said optimal bias decisions are, well, I compute for each action the cost, the expected cost of that action, and then I select the action which has the lowest cost. Now let's see how this translates to a binary problem. In a binary problem, we have, as we said, we can parameterize the problem with a cost matrix that has zero cost for the correct predictions and a non-negative cost for the false negative and false positive errors. So let's see how our recognizer should make its decisions in this case. Now, here we have two possible labelings. We have label as true, or here is HT, I was using just T in the last slide, so you can call it just T if you want this one, and label as F. It's true hypothesis and false hypothesis, or just true and false. So the cost, we can measure the cost of labeling a sample as true, and the cost of labeling the sample as false. Of course, this depends on the sample and the recognizer. That's why we have X and R below. Of course, we have a recognizer that gives us a class posterior probability for true and false. So the recognizer gives us these two, or actually just one, because the probability of false is 1 minus the probability of true. That's exactly what we did for binary problems up to now. We computed one posterior probability and then used that to compute ratios that had, well, we computed scores that were represented ratios of probabilities, but we saw that we could represent everything with a single number because actually the two class posterior probabilities are related. So we can compute the cost of the actions when the classifier gives us these values for the posterior probabilities. Now, if I assign label true, what do I have? Well, let's see, start with true. If I assign predict as true, I have that if the sample is true, I pay 0. So here I have 0 times the probability that the sample is true. And then what I pay? If the sample is false, I pay a cost of false positive. What is the probability that I will pay the cost of false positive? According to the recognizer, that's the probability that the sample is false. Here I'm assigning label true. So if I decide to label the sample as true, then there is this probability that I will be wrong, because that's the probability that the sample is actually from the false class. And in that case, I will pay a cost equal to the cost of a false positive. False positive I predict as true, positive, but it's wrong, so false. If I assign label F, what do I have? If the sample is from class F, I will pay 0. What is the probability that the sample is from class F? Is this, according to the classifier. What is the probability that the sample is from class true, and how much will I pay if it's from class true? I will pay the cost of a false negative. So we have a cost of false negative times the probability that the sample is from class true. Now, of course, these two go away. What I get is, if I assign label true, then I pay a cost that is cost of false positive times the posterior probability that the sample is actually from the other class. And if I assign class false, then I have a cost, expected cost, that is the cost of a false negative times the probability of having a false negative. This is the probability of having a false negative if I assign class F. The probability of having a false negative if I assign class F is exactly the probability that the sample is from the true class. Now, I need to make my decision, so the posterior probabilities are given by my classifier. So the classifier gives me the posterior probabilities for the two classes. I have the cost from the cost matrix. I will compute these two values, and then what I will do, I will choose the action that has lowest cost. So if this upper cost, if this cost is lower than the second one, I will assign class true. If it's higher, I will assign class false, which means that, you have it here, if this term is lower than this, I will assign class true. If the second term is higher than this, I will assign class false. This is the probability, the cost that I have if I make the two kinds of mistake weighted by the probability that I will make that mistake. And I don't have an equal here, but you can put the equal in both cases. We don't prove it, but from the point of view of bias decision and from the point of view of optimizing empirical bias risk, where you put the equal is irrelevant. So we don't specify how to resolve tie breaks, so where the two costs are equal. You just need to define a rule that is consistent, and then you will not have any. From the point of view of optimality, there will not be any consequence on where you put the equal. Of course, from practical points of view, you may have one more or less error, but from the point of view of the discussion that we make, we don't have any way to prefer one label to the other, so both cases are the same. So for example, you can put the equal here. Now, this looks similar to what we had with when we started making label assignments without taking into account costs. There we had that essentially we said if the posterior probability of one class is higher than the other, then we assign the corresponding class. Now this is similar, but this time we have also the contribution of the cost. Notice that, of course, if the costs are equal, we end up with the same assignments that we had before. When the costs are equal, then it's just the posterior probability that matters, because the cost of the different errors are the same, so they don't matter because any error costs in the same way. So we will try to minimize the number of errors that we make. As we did last time, we can rewrite this as how, well, the if part can be rewritten by taking, these are all positive values, so we can divide both sides without changing the side of inequality. So we'll have 1, if this holds, if this holds with minor, then we'll assign class true. If this holds with greater than, then we'll assign class false. Notice that the two conditions are the same. What changes is just the sign of the inequality. Again, rather than working with ratios, we can take log of both sides, which means that we will assign class h true when the logarithm of this part is actually greater than 0, logarithm of whatever was inside. We will assign label true. If this is lower than 0, we will assign label false. And if it's equal to 0, then you can decide any assignment. So essentially, we need to compute this term here, this ratio here again, that looks similar to the ratio that we were computing before. It's a posterior ratio. Actually, it's the posterior ratio that we were computing before. F. Plus a logarithm term that contains the ratio of the two costs, the cost of the two errors. And we observe already here that what matters is the ratio of the two costs to make the decision, because they appear only as a ratio. So what really matters is not the absolute value of the cost, but the relative values, or relative value of the cost of the two errors that we can make. In any case, this was the class posterior ratio that before we were comparing with 0. Now we can compare the class posterior ratio that we were using before with what? Well, now we compare it with minus logarithm of cost of false negative divided cost of false positive. We want to compare R with 0 to make our decision. R can be expressed in this way, which corresponds to taking our posterior ratio and now comparing it with a value that depends on the ratio of the two costs of errors. Before we were comparing it with 0 before we introduced costs, and we said comparing with 0 gives us optimal decision when the costs are the same, which is true, because if the costs are the same, then I have logarithm of 1 on the right, so this becomes exactly 0. If the costs are not the same, it will change the threshold at which I should threshold my class posterior ratio. Notice that these are the ratio of class posteriors. Then we can do one more step, and for generative models, we can actually cast this as a comparison not of the class posterior ratio, but directly of the log likelihood ratio. What does it mean? It means that this holds true for any model that gives me class posterior probabilities. So if a model gives me class posterior probabilities, then I can apply these expressions and get optimal decisions. Then we have said, when we were discussing generative models, we have said that while in the case of uniform errors, this was a way to assign probabilities, assign class labels, we said that if we have a generative model, we show that what we can do is to compute a log likelihood ratio, that is the log ratio of class conditional probabilities, and compare it with a threshold that depends on the prior probabilities. Why? Because for a generative model, we can represent this as, remember that the posterior probability for a generative model is the class conditional probability times the prior probability, so this divided the marginal. Okay, this is for a generative model how you compute class posterior probabilities. You have your class conditional density, you have the prior, and then you have the marginal that we said we don't really care, because when you compute the ratio, it disappears. But if I put this here, I get that the first term is class conditional times prior divided by marginal. The denominator is the same, but now with the reverse fraction. So the class conditional is below, the prior is below, and the marginal is above. The two marginal simplifies. And then I compare this with 0. So I have log of the class conditional ratio, so log likelihood ratio plus log of the prior probabilities compared with 0, which means, now let's call the prior probability for true pi, the prior probability for false is 1 minus pi, because the two must sum up to 1. I bring this on the other side of the equal. This is called log likelihood ratio, the score S, or if you want, log likelihood ratio of X, that is our score. Let's remove, I didn't put the T, so let's remove this T. Just X. Okay, here I was putting xt, but then everything is written in function of X, so let's remove the T. Is log likelihood ratio compared with minus log pi divided 1 minus pi. This was how we were doing the classification last week for the Gaussian models when we were working with binary models, with binary problems, computing log likelihood ratio and comparing it with a threshold, which corresponds to comparing the class posterior ratio with 0. Of course, when we introduce cost, we have seen that this becomes, it's not 0 anymore, but it's what we have it in the previous slides, is minus logarithm of cost of false negative divided cost of false positive. If we redo all the computation, we can show that we can again represent the problem as a comparison of a log likelihood ratio with a threshold, but in this case, the threshold will not just be this term, but it will also need to account for the additional term here. Essentially, we will need to add here minus log of cost of false negative divided cost of false positive. But if you want, we can do it starting again from the definition of the ratio. We write what the ratio is cost of false negative times posterior probability. So we just rewrite this as cost of false negatives times class conditional for class true times prior for class true divided the margin, but the margin simplifies, so I'm not writing it. And below I have cost of false positive times class conditional for class false times prior probability for class false. Now let's rewrite this on this side of the expression. Then what I have, the logarithm of the first part of the fraction is the log likelihood ratio, and this is the second term that depends on the prior probability and the cost of false positive and false negative. So I can split the expression in what? I have a class conditional probabilities and a term that depends on the application that I want to optimize for, prior probability and cost of errors. Then my goal is to compare this thing with 0, which means that my decision will become compare the log likelihood ratio with minus the log ratio of prior log odds and cost of errors. If you want, you can write this also in this way as we did before. It's the same thing. So our threshold has changed to take into account the cost of the different errors. If my classifier gives me a ratio between class posteriors, then the threshold that was 0 becomes just minus log of the ratio of the two costs. If I represent, my classifier gives me a log likelihood ratio, then the decision rule becomes comparing the log likelihood ratio with a threshold that looks like this. This is the threshold that will optimize my decisions according to the recognizer posterior probabilities. So for the given prior, remember that the posterior probabilities depend on the prior, because the prior affects the posterior probabilities. So it's correct that my comparison depends on the prior, because what I'm comparing originally was posterior probabilities that depend on the prior. Here, the prior was hidden inside the posterior probabilities, but the posterior probabilities for a generative classifier are a class conditional times the prior. things will get a bit more complex when our models will just give us these terms without explicitly modeling the prior probabilities, but we will discuss it later. But in any case, the prior is in some way embedded into these posterior probabilities that must take into account the prior. If we look at it from the point of view of log likelihood ratio, the log likelihood ratio is prior independent, so the prior needs to be somewhere, and we see it appearing in the threshold in part. So the log likelihood ratio, once more, allows us to separate a score that does not depend directly on the application. What's on the left of that inequality is something that depends on the model, but to compute it, you don't need to know anything about your application, so this is application independent, this part, and all the application information can be put inside the threshold. For generative models, for models with output at low likelihood ratio, this is a good property because this one I can compute even if I don't know my application, and then I will just need to change the threshold to adapt my model to different applications. So a generative model has the advantage that once I train it, once I don't need to specify in advance my application, I can adapt my model to any application by simply changing the way I threshold my log likelihood ratios. Classifier that gives me a log likelihood ratio gives me a score that is application independent, and then I can adapt that model to take optimal decisions for different applications by simply changing the decision threshold that I use, which itself will depend on the application. So once more, we have this kind of property, but this threshold now is application optimal. So it's optimal for a given application, while the score is independent on the application. As yesterday, we can see that the application information is all condensed into the three values: prior probability, cost of false positive, and cost of false negative. However, notice that these appear in a way that, well, they are not independent. What does it mean? For example, we have already seen that the cost of errors does not matter on its own. What matters is just the relative cost. So if I have an application where the cost of false positive is 1 and the cost of false negative is 2, and an application where the cost of false negative is 10 and the cost of false positive is 20, the decision will be the same, because the ratio will always be, I don't remember which I said, positive or negative, but the ratio will always be 1/2. So the costs do not need to be specified in a way that is necessarily an absolute cost. What matters is that we are able to specify the relative cost of the two errors. That's why we never use actually unit of measures for the cost. It doesn't matter. What matters is just the relative cost of one error with respect to the other. We can do it, you can do even a slightly wider step. We can show that of those three, so we already showed that of those three numbers, actually one is irrelevant. That is, this application will always be equivalent to the application that has these costs. If I divide both costs by the same constant, then I get the same decision. So those three numbers, actually one is already relevant in the sense that I can fix it to 1 and build an equivalent application that has the same decisions. Then if you remember yesterday at some point, we made a strange transformation and we said, let's consider an application with a strange prior that was obtained by applying this expression over the triplet that defined the application. And we said yesterday, we noticed yesterday that using that transformation, an application which had this, sorry, the parameterization, okay, here it's called negative, but it doesn't matter if you put before the false positive or the false negative. So if we have this application, and you consider the second application obtained by using this new prior and the cost of errors equal to 1, we observed yesterday that in terms of normalized detection cost function, the two applications would have the same normalized cost. Notice that we already said that the costs are useful as a relative measure. So we are already saying if the cost represents a relative measure, then the non-normalized DCF loses its interest because what matters is just a relative cost of the different systems. And in that sense, we show that if we look at the normalized version of the DCF, then these two applications are the same. Why this matters? It matters because we can show that this holds true also for decision making. If we take an application with this cost and this prior, and we consider an application with the effective prior defined in this way and the cost of errors equal to 1, what do we get? Well, let's take optimal decision for the second application. What does it mean? It means that our threshold is what? Is minus logarithm of pi tilde divided 1 minus pi tilde. The cost of the errors are 1, so in this case they cancel out. But this pi tilde is what? Pi t cost of false negative divided all this ugly thing. You have it on the slide, so I will not rewrite it because it's kind of troublesome. You have this term is pi tilde, and this is 1 minus pi tilde. Then you extend this ratio here, you do the computations, this below becomes pi t CFN plus 1 minus pi t CFP minus pi t CFN divided whatever was here. These two simplify. In this ratio, the denominators become the same, so they also simplify. What I'm left with is this expression, which means that minus log pi tilde divided 1 minus pi tilde is equal to minus log pi t 1 minus pi t cost of false negative divided cost of false positive, which is what is the threshold for the original application. So from the point of view of an application, using the making optimal decision for this application or for the original one gives us the same answer. So what are optimal decisions for the original applications are also optimal for this new application. And in terms of normalized DCF, what I get evaluating my system for the original application is the same that I get evaluating my system for this, let's say, equivalent application. Which means that from the point of view of evaluation, normalized DCF, and decision making, these two applications are the same. They represent the same application. They have lead to the same decisions, and the normalized costs are the same. Now, this shows us that this means that we can represent everything with a single value. We call this value effective prior. Why effective prior? Because it behaves like a prior probability. It's not really a prior probability in the sense that it doesn't represent the probability that a sample will belong to that class in the application. But it represents a probability such that if my application had this prior probability and costs of errors are uniform, then I would make the same decisions as what I would do when I have the real prior probability of my application and the actual cost that I measured. Which we can see that essentially the cost contribution can be interpreted as if I increase the cost of one kind of errors, it's similar as if I was increasing the corresponding prior probability. If a class is a higher cost, that's equivalent to a problem where that class is actually more represented than it's really represented in the application. Which makes sense. If I have more points of a class, that means that I want to have fewer errors for that class, because if I have more points of that class, I want to minimize the errors of that class. That's similar with the cost. If a class, for a class, the cost of error is higher, I want low number of errors for that class. is the thing that is being written here. This effective prior allows us to represent all applications with a single number, and it's useful because we will see it allows us to compare how the system would work on many different applications as a function of the application. What does it mean? It means that for binary problems, since we can represent all applications with just one value, we can make plots where we have on the x-axis the application parameterized by the effective prior, and on the y-axis, for example, the bias risk that we would have for that application, which allows us to evaluate not just one application, but graphically evaluate how the model would perform on several different applications. This is kind of similar to ROC curves, but the advantage with respect to ROC curves is that in ROC curves, we were just computing trade-offs between the different kinds of errors. Here, we are considering specifically all possible applications of interest and computing biased errors for those applications. And we will see that in a moment. Okay. Let me see what time is it. Okay. Now, of course, what we said is, so this is what I said, for probability generative models, we can then cast the problem as a problem where we compare with a threshold, which is either the threshold that depends on the cost of the different errors, cost of false negative and cost of false positive, or as a threshold that depends just on the effective prior which embeds inside the two costs. Now we will see models where the classifier itself gives us a score which does not have this probabilistic interpretation, which means that the threshold that we just defined does not lead to optimal decisions anymore. We say in this case that the scores are miscalibrated, which means that if we were to use the theoretical threshold that we know is optimal for log likelihood ratios, we would actually end up with a cost that is typically much higher because the score itself does not behave properly, so it does not give me the correct solution when I use the theoretical threshold. For example, imagine that I have a system whose score is just 1/2 the log likelihood ratio. For this score, I would need to use 1/2 of the original threshold for comparison. Otherwise, if I use the original threshold, I'm not getting the correct answer anymore. Remember, if I have, this is my log likelihood ratio, this is a function of the prior, and this is the log likelihood ratio. If rather than the log likelihood ratio, I have a system whose score is 1/2 the log likelihood ratio, then the optimal threshold for this t prime would be 1/2 the original t. If I use the original t with s prime, then I'm not doing the correct thing anymore because I'm using a threshold that is twice the one that I should use. So I'm not optimizing for the correct application anymore. Which creates problem because in many cases we have miscalibration. We have miscalibration for models that are non-probabilistic, for example, supervector machines. But we also have miscalibration when there is mismatch between the training set and the application data. We may have miscalibration when there are assumptions that are not accurate for our model. So for example, we have data that is distributed in this way, and we approximate with a Gaussian distribution. That may lead also to calibration issues. Which means that in many cases, our original threshold is not optimal. We'll see how to make it optimal again, but it will take some time. To make it optimal again, we see at the end of the course a set of methods that are called calibration methods that essentially transform a non-calibrated score into a score that behaves like a log likelihood ratio so that then we can use the theoretical threshold anymore. So in that case, we will be able to use the theoretical threshold, compute our predictions, and compute our empirical cost. Now, since this is a problem that affects several classifiers and results in our cost being higher than what they should, but typically this is not due to the fact that the classifier is not able to distinguish the classes, but it's just not producing scores that we can threshold in the right position for the application. So for example, you can imagine you have a classifier that gives you linear separation rule. We have seen that changing the threshold corresponds to changing the position of the separation rule. The classifier may give me the correct separation rule, but just, so the correct orientation of the hyperplane, but it may not choose the correct surface among all possibilities. Which doesn't mean that the classifier is weak. It means that we just need to adapt our threshold to get the optimal classifier. Now, for binary problems, we can measure these two effects separately. So we can measure how good the classifier would be if the threshold was optimal, and how much we lose because we're not using the optimal threshold. To do this, we define a new matrix that is called the minimum DCF, minimum detection cost. That is the detection cost that I would have if I were to use the optimal threshold over the evaluation set. So I have an evaluation set. For this evaluation set, what should I do? Up to now, we said I should run my recognizer. My recognizer should do what? For each sample, give me my prediction, and the prediction is a function of the threshold, okay? So of the application that I'm optimizing. And then for the same application, I will compute the bias risk. The minimum DCF does something a bit different. It takes the recognizer. The recognizer gives me just the score, and then I compare it with a threshold that is optimal according to the evaluator itself. So the best threshold I can use. Rather than using the theoretical one, I use the optimal that minimizes the evaluation results. This we call minimum DCF. It's the best value that we could have for the bias risk if we were able to choose the best threshold for the evaluation data. How do we do it in practice? Essentially, we will consider all possible thresholds, compute the DCF for all possible thresholds, and then take the minimum one, which, if done efficiently, is actually may look complex, but it's actually fairly quick. And then we will select the threshold that gives us the lowest DCF when that threshold is used to make our decisions. Of course, this is not an unbiased evaluation. This is very biased because I'm estimating the threshold on the evaluation set itself. So this is not a real cost that I will pay for my data. This represents a lower bound of the cost that I pay. I know that even if I'm able to select the best threshold possible, I will not pay lower than this. Why this is useful as a metric? It's useful because typically it's not that hard with the tools that we see to bring the real cost close to the minimum one. Now, since we see that computing calibration results make the system much more complex, typically it's useful to build a classifier by comparing minimum costs, then select the classifier that has minimum DCF, and then address the calibration issues afterwards. So the minimum DCF is useful to compare the potentiality of the classifiers without taking into account miscalibration issues of the classifier. As we said, this is not an unbiased evaluation, but since typically to reduce the gap between the minimum DCF and the actual cost that we would pay if we were using the theoretical threshold is not that complex, we can reach quite close results. That's a good proxy to decide to compare different classifiers to decide which is better without having to do the whole machinery, including calibration, for the evaluation. So this is a reason why this kind of metrics are used, and we will use it in the project as well, because we will introduce calibration only at the end. So we will need a way to select which classifier we want to bring to the end of the project before we actually know how to calibrate it, because otherwise we would have to do everything after the course is over. Of course, this DCF is the DCF we would obtain with an optimal threshold. this is not what we will pay, but it's a lower bound on what we will pay if we use any other threshold, including the theoretical one. The difference between the actual threshold, the actual DCF, the one that we defined up to now that is computed with the application prior, with the threshold corresponding to the application effective prior and the minimum DCF, is called also miscalibration loss. It's how much worse my results are because I'm not able to select the optimal threshold. So in some sense, the minimum DCF represents the discrimination power of my classifier, how much it's able to separate my two classes, and the calibration loss is how much worse my results will be because the classifier would be able to divide the classes, but I'm not able to select the correct threshold among those that the classifier would allow me for. Finally, as I said before, having for binary problems a single value allows us to compare systems over different applications with plots that are called bias error plots. As I said before, these are plots where we parameterize an application by a prior pi tilde, and then given application for a prior pi tilde, we can compute the corresponding minimum and actual DCF with the two procedures. Actual DCF means we take the scores, we compare it with with the threshold that depends on pi tilde, and then we compute the DCF using pi tilde as metric. Minimum DCF, for all the thresholds, we compute this procedure, and then we select the cost that corresponds to the optimal threshold. So in one case, the pi tilde is used both for the threshold and for the computation of DCF. When I use minimum DCF, I'm using pi tilde to compute the DCF, but the selection of the threshold is done by first running all possible options for that specific pi tilde with all the possible thresholds, and then selecting the threshold that gives me the best value. What we would get are plots that look like this. As a function of the prior, we will get the different costs. Now, as we said, the prior is used as a threshold, so since this threshold has a nice property of being, well, the minus prior log odds is symmetric with respect to the two classes, in the sense that if I reverse the role of the two classes, I get just minus the original threshold. So we have seen that it's unbounded. It goes from minus infinite to plus infinite and so on, rather than parameterizing here on X the application with pi tilde, we parameterize it with the logarithm of the prior log odds. Notice that it is minus the threshold. So here, rather than having a linear axis in pi, we have an axis that represents the prior log odds themselves. So log of pi divided 1 minus pi. It's just a change of the scale of the axis. Then, for every value here will correspond to a pi, because if I have this actually equal to x, means that for each x, what do I have? Pi tilde divided 1 minus pi tilde equal exponential of x. I can solve this. We will do it after the break. And this will be a function of x, which is called sigmoid. But we will see that later. So not important now. But just to say that for any point here on this axis correspond to 1 and a single 1 prior probability pi. So it's a parameterization of the application. Then for each application, I can compute actual and minimum cost. Of course, we observe that the minimum cost is always lower or equal than the corresponding actual. Each of these points represents a different application. For an application, we said the minimum cost is the cost that I would get if I select the optimal threshold. The actual cost is a cost selected, obtained with the threshold that corresponds to the application. In this case, minus what you have on the x-axis, this pi here, actually pi tilde all these are pi tilde because we use the effective prior. So for any application, each x corresponds to an application, the corresponding mean DCF is lower or equal to the application. Then we can see that we have this V-like shape. These are normalized DCF. With normalized DCF, we can show that actually the minimum will be corresponding to this point 0, and then the DCF, and the minimum DCF will increase as we move far. What does it mean? We move far from 0. 0 corresponds to a prior log odds that is 0, which means that the effective prior of the two classes is the same. So it's as if the cost of the classes is the same, of the errors is the same, I also have the same probability of the samples belonging to the two classes. So the two classes are perfectly balanced, both in terms of cost and prior. Or if they are not balanced, then the cost effects and the prior effects cancel out, and the effective prior would be balanced. If I move on the right, it means that pi goes towards 1. If I move on the left, it means that pi tilde goes towards 0. So the effective prior for class 1 is increasing, so I have more and more unbalanced applications. The farther I am, the more unbalanced my applications, which also show us that we'll not see with unnormalized DCF, unbalanced application will result in a lowering typically of costs. But with normalized cost and measure how good our classifier is with respect to not using the classifier, we see that the more unbalanced are the classes, the harder it is to do better than not using the classifier. Our DCF, minimum DCF, will grow in this V shape. We can prove that as we move, they need to grow, they cannot go down, which means that the more we move away from a balanced application, the harder it is typically for a system to do better than not using the classifier. It makes sense. If my prior probability for class 1 is 1, it means that all the samples are from class 1. I cannot do better than a classifier that always says class 1, because all the probability that the sample is from class 0 is 0. So whichever classifier tries to label as 0 will make a mistake according to my prior probabilities. Finally, of course, actual DCF are not strictly increasing. Finally, why do we drop at 1 here? Well, 1 represents the point at which the classifier becomes useless. Mean DCF will always be lower or equal than 1, because in any case, when we optimize the threshold, among all possible thresholds, we always have the solution where all the scores are below 1 the threshold, or all the scores are above the threshold, which corresponds to one of the dummy systems we have discussed. So mean DCF, by definition, cannot grow larger than 1. Actual DCF can. And when actual DCF grows larger than 1, it means that our system for those applications is actually harmful. Finally, this gap for any application is the calibration loss, the distance between what we could achieve if we are able to select optimal threshold and what we achieve in practice. So for these two systems, we can say that, for example, the first system corresponds to scores that are not well calibrated. We have good calibration only in a small range of applications. So the system works well for applications in this range, but has a large loss for other applications. Notice the large loss, I mean, you can even have double the error. So calibration loss may be significant. It may make your errors be twice, 3 times what you would want them to be. The second model shows good calibration. The actual costs are essentially overlapping with the minimum. The cost that I pay because I use the theoretical threshold rather than the optimal one is almost 0, because the optimal threshold for these scores works well for most working points that we are considering here. We can show that actually these scores that look like this are well calibrated, but this goes beyond what we will actually do. So we'll not be able to relate the distribution of the scores to the calibration of the scores, but we will try to say a couple of things near the end of the course. Okay, let me see if there is anything else. Okay, as I said, we will use calibration approaches to compensate this, but this we will have this same slide at the end, so we can just skip this last three slides because we'll see them again at the end of the course. So we can stop here. These three slides, you can skip them. If you want, you can read them. You will have the same slides in the last lectures in any case. So that's all. Questions? Okay, then a few minutes break for those who have the laboratory now, and then we resume.